This is the end of Chapter 6, the end of the gas laws. So we're going to go over Dalton's law. Actually, I should have put this dude's name in, Graham's law. And then a little bit gas stoichiometry using the 22.4 liters per mole that we've encountered. All right, so we're going to start with Dalton's law. And you may remember me saying prior that all gases mix together to make homogeneous mixtures or gas phase solutions. They are not selective. Remember, there are not any significant intermolecular attractions or repulsions, no intermolecular forces in general between gases. And so they mix homogeneously, always. Now, Dalton's law says that the total pressure of a gas is simply a sum of the individual partial pressures of all the gases that make up the total pressure. The total pressure in most of the problems we'll be working on is simply atmospheric pressure. Okay, so if you're doing an experiment out in the open, like not in a sealed container or something, then atmospheric pressure is total pressure. There is an easy way to find the partial pressure of a gas if you know the mole fraction of the gas in the mixture. So it's a new formula for us, but of course mole fraction or any type of fraction is the portion of what you're interested in over the total amount. So here's an example. Let's do something with Dalton's law. The partial pressure of nitrogen in air is 592. Remember I said atmospheric air pressure serves as total pressure unless you're doing something in like a sealed container or something. So the total pressure is 752. What's the mole fraction? So let's rewrite our formula first. The partial pressure of nitrogen equals the mole fraction of nitrogen times the total pressure. All right, so let's fill in what we know. Doesn't matter the units as long as they match on both sides because the units are going to cancel. So 592 torr. We're trying to solve for the mole fraction of N2. All right, so that's how you set up. We're going to divide both sides by 752, right, so that we can solve for the mole fraction. And here you go. So the mole fraction of nitrogen in air is 0.747. Use your common sense when you work these problems, right? So mole fraction has to be less than 1, right? If it's 100% one component, then the mole fraction is going to be 1. So just make sure you get something less than 1. Here's an application of Dalton's law that's a little trickier. Gases are very commonly collected. So we have let's say we have here's a good example, the picture. A reaction between zinc metal and acid, hydrochloric acid. It produces hydrogen gas. How do we collect that hydrogen gas if we want to? Well, one of the most common ways is to bubble it through water. You can put an inverted container in a bin of water, fill the inverted container all the way up with water, and then because gas is less dense than water, it's going to go to the top and displace the water. And then at the end, you have this container full of the gas you're trying to collect. The issue with that is when you do collect a gas over water, the gas is contaminated with water vapor. And so if you're trying to get properties of the gas or purify it, you've got to account for the water vapor. So using Dalton's law, again, we could say, okay, as always, the total pressure is equal to the pressure of the gas we collected, in this case hydrogen, plus the partial pressure of water vapor gas that has contaminated it. And then rearranging it, okay, if we want to solve for the partial pressure of just the gas we collected, it's the atmospheric pressure minus the pressure of the water vapor. Now, there are tables of values for water vapor pressure at different temperatures, so you can easily look those up. This slide is just typing out what I said on the previous, but I'll leave it because I know some of you learn better by reading than by listening. So here's a typical table of vapor pressure of water. And again, the primary thing that changes it is temperature. So what you do is you pick the temperature at which your experiment took place. So let's say it was room temperature, 25 degrees Celsius. You would look and say, okay, the vapor pressure of water at 25 degrees Celsius is 23.78 millimeters of mercury. And then you could go back to Dalton's law and subtract out that portion of low vapor pressure. So let's work a complete example here. We collected dinitrogen monoxide over water. So that's your signal that you've got to use Dalton's law. And we're looking for the volume that just the dinitrogen monoxide occupies, okay? So anytime you collect a gas over water, the very first thing that you want to do is find the pressure that's due to just that gas. So let's go ahead and quickly do that. And then you'll use the ideal gas law to find the rest of the information you need. All right, so the total pressure or atmospheric pressure is 0.928. We're trying to find the partial pressure of N2O, and the vapor pressure of water at the temperature which we collected the gas is 21 torr. Double check your units, okay? Notice that the vapor pressure of water in this case is in torr, and the atmospheric pressure was an atmosphere. So they've got to be, doesn't really matter which unit you use. I'm going to switch them both to atmosphere because I know I'm going to use the ideal gas law, which is going to need atmosphere based on the R value I use. So let's see. If we have 21 torr, the conversion factor to atmosphere is there are 760 torr per atmosphere. And so I'm going to go ahead and pull out my calculator and see what that is. Okay, so that is not very much, 0.0276 atmospheres. All right, so then rearranging this equation, we can find the partial pressure of dinitrogen monoxide. It is 0.900 atmosphere. So now we're going to go to the next slide and use the ideal gas law. All right, so there's just what we did in the last slide, a little bit neater. Now this question asks us for volume, so we're going to start with the ideal gas law. We're going to rearrange it to solve for volume, plug in all the values we have, and here is the volume of just the dinitrogen monoxide we collected. Okay, so let's move on to doing some stoichiometry that involves gases. So the conversion factor we are interested in here is converting between moles and volume of gas. This conversion factor, that 22.4 liters of any gas contains exactly 1 mole of gas, can only be used for gases, okay? That is not true for liquids. If we're doing conversions to volume for liquid, we need density, okay, grams per milliliter. Alrighty, so let's do some of those. All right, so here's a reaction that involves gases. It's actually a fun reaction. I don't know if you've ever seen it maybe in high school chemistry, that you can take some hydrogen gas, and of course there's always oxygen gas in the air, and if you get it a little catalyst, like a spark, a little flame for a second, it actually explosively reacts to make water. But anyway, they're all gases, and so that's when we can use a conversion factor of 22.4. So with all stoichiometry problems, you're going to start with the given information, which is 1.24 liters of hydrogen gas. All right, I don't think we're going to, well, yeah, we do need that. I'm glad I thought of that. So the equivalency 22.4 liters equals 1 mole is only true under STP conditions, okay? As soon as you change temperature or pressure away from STP, the amount of molecules in a certain volume of gas changes. All right, so now we can go to, where are we trying to get to? We're trying to get to water. All right, let's go ahead and convert this liter out of moles so that we can use a mole ratio. Okay, so now we're moles of H2, and let's go ahead and use the mole ratio. So let's see, for every 2 moles of hydrogen gas, we form 2 moles of water, 1-to-1 mole ratio, okay? And let me pause just a minute, figure out how many. You can do a long run-on conversion. I just kind of wrote too big and ran out of room, so I'm going to go ahead and get an intermediate answer. Okay, so we have 0.05536. That's more digits than I need, but this cancels, and we are with moles of H2O now. Okay, so we're trying to get to grams of H2O. So we need molar mass, and we know that for every mole of H2O, its molar mass is 18.02. And so now we have 0.9975 grams of H2O. And here it is, worked out all prettily. So we've gone briefly over Dalton's law, briefly over gas stoichiometry, and the last hot topic in this PowerPoint, as well as the whole chapter, is learning about effusion and diffusion and Graham's law. So this was a really cool GIF, but when I uploaded it to lecture, it's not working anymore. But anyway, diffusion, effusion. So we're going to start out by defining either of those. Diffusion is just the spreading out of gas particles. So, for example, if you're over here and you squirt, let's say perfume, a little squirt of perfume. These, and by the way, in order for humans to smell anything, particles of that substance have to be in the gas form so that they get in our nose up to our olfactory senses. But so if you spray perfume, these particles of gas are going to diffuse or spread out, okay, and be moving across the room. So at some point, that's why somebody on the other side of the room can eventually smell them. Effusion is when you have a hole in something that's sealed, essentially sealed, and gas escapes through the tiny hole. So that would be like a nail in your tire or a balloon. That's why the balloons, the cheap latex balloons, will shrink down to nothing because they keep the gas in for a while, but they have little tiny holes in them, and so eventually all the gas escapes out by effusion. So Graham's law says that the speed, the velocity at which a gas particle travels translationally, that is like across the room, is inversely proportional to the square root of its molar mass. Okay, so in general, if you're comparing different gases, right, as the molar mass of a gas goes up, as it gets heavier, its speed is going to go down. That's kind of intuitive for us. Okay, but that is true for gases too. So now the root mean square speed or velocity is also dependent on the temperature, right? So just as you would expect, as temperature goes up, the speed or velocity of a gas particle is going to go up also. It's important to be able to understand the relative velocities of gases, be able to construct and interpret this type of graph. So if we have the y-axis is the proportion of gases that have this velocity. So just like you might have a bell curve for the distribution of grades in your class, right? So the y-axis would be the proportion of students with a certain grade, okay? And so this might be average C. And so the highest proportion of students would have the average grade of C. So this is how this works. So let's look at oxygen gas. So for oxygen gas, the highest proportion of molecules in oxygen gas at a certain temperature, because we're not varying temperature, see, we just have velocity on the x-axis. But the largest percentage or fraction of molecules of oxygen have a speed of around 250 meters per second, right? Now, the average or the highest proportion of nitrogen molecules at this same temperature have a speed under the same conditions of closer to maybe 350. Okay, so you can see the trend here that as you go this way, the speed is increasing, right? So if you were to order them from slowest to fastest, the slowest would be oxygen, and then nitrogen, water, vapor, helium, and hydrogen. And you might notice, hopefully, that the molar mass goes in the same order, okay? The molar mass is increasing going to the left. So the smallest, lightest molecule is the fastest. Also notice how they're spread out more, right? As they get to be faster, like look at hydrogen, look how spread out the distribution of speeds that the hydrogen molecules have in a group. Now, Graham's law simply takes the formula for the root mean square speed that we had, which was temperature over molar mass, and made a ratio, which the kind of extraneous variables cancel out, and it's much easier to use. So if you're taking a ratio of this formula for two different gases, the constants are going to cancel out. Now, if you're doing them at the same temperature, then the temperature cancels out too. And it simplifies to the rate of effusion, and this works for diffusion also, any type of translational motion of a gas, traveling across from one side of a room to another, is inversely proportional to the square root of the molar masses. So what I want you to notice out here, an easy mistake to make, is remember it's inversely proportional to molar mass. So gas 1, its molar mass goes in the denominator. Gas 2, the molar mass, okay, they're diagonal from each other. Also, do not forget that you need to take the square root of these molar masses. That's also easy to overlook. Here's a sample problem. Now, probably the trickiest part is to know how to set up your ratio. So let me just write a simplified expression of Graham's law. Okay, so you got to make sure you put the right things in the right place, right? All right, a compound effuses, that's what tells you it's a gas, through a porous cylinder. So it's effusion, it's squeaking through little holes in the little pores, 3.2 times slower than helium. So what's going to be the fastest gas? I like to put the fastest gas on top. so I don't have to deal with fractions less than 1. So from the wording, you can tell that helium is the fastest. So I'm going to put I'm going to put helium on top. Rate of helium versus rate of some unknown gas, okay? And I know that helium is faster by 3.20 times. So here's my rate. So I've got helium on top, so its molar mass goes on the bottom, and the molar mass of the unknown goes on top. Okay? So instead of putting in individual rates for these two, more frequently than not, the problems will give you the ratio automatically. You just have to straighten out what goes on top, what goes on bottom. Just read it carefully. All right, so once we simplify to solve for the molar mass of the unknown gas, right? We already have the ratio here. Raised to the 1/2 power, hopefully you remember from that math, that's equivalent to square root, right? Just another way you can do it on your calculator if you want. All right, so we want to solve for the molar mass, so we're going to multiply both sides by the square root of 4, right? That'll cancel. Square root of 4 we know is 2. So now we have 3.2 times 2 equals square root of the molar mass of the unknown gas. Okay, multiplying these two together, 6.4. So now we have square root of the molar mass of the unknown gas equals the square root, equals 6.4. Okay, so just square both sides and get rid of the square root. Okay, so now we have molar mass of X is 6.40 squared. So the answer is 41. And that is it. So now you just need to practice a bunch of them.